Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 16 on the differentiation operator.
You may have come into this class thinking of derivatives in terms of numbers or slopes, but we've broadened our perspective by thinking in more abstract and conceptual terms. We're going to culminate that process in this lesson by thinking of differentiation as an operator. This more global perspective is going to lead us not only to better comprehension, but better computational abilities.
Some derivatives do not follow from the basic rules that we've covered thus far. For example, what's the derivative of 2 to the x? If you don't recall, you may be tempted to write x times 2 to the x minus 1. That would be a mistake. That is not the derivative. What about some other functions? Arcsine of x. Do you recall the derivative? That. What about x to the x? Or x to the x to the x? Or more complicated functions still. These can be differentiated, but we cannot use the basic rules that we've learned thus far. What we will use is the idea that differentiation is an operator and that it acts on equations as well as functions, and more importantly, it works well with other operators such as exponentiation or integration, taking a limit, or in particular, the differentiation operator works well with the natural logarithm operator. And that is the basis for that method known as logarithmic differentiation. Let's begin with a simple example. Compute the derivative of e to the x. Now, I know that you know what that derivative is, but let us compute this via logarithmic differentiation. The key step will be to write e to the x as y, and then to simplify this equation, we'll apply the natural logarithm to both sides. On the left, we obtain log of y. On the right, log of e to the x. That is x. And now we can differentiate this equation. On the left, we'll obtain dy over y. On the right, we'll obtain dx. And by manipulating these differentials, we can easily compute dy dx to be y. That is e to the x. Now, this process is simple enough, but step back and think of what you're doing. What we're really doing is taking our initial equation and applying the natural logarithm operator and feeding the results of that into the differentiation operator. That is what allows us to compute this derivative. Now, you can compute other things similarly. For example, you could show that the derivative of a to the x, where a is a constant, is a to the x times log of a. And that's a fun exercise. But there's more to logarithmic differentiation than just this. In fact, applying operators gives lots of examples of things that are not quite logarithmic differentiation, but follow a similar pattern. For example, let's look at the derivative of log of x. Now, we both know the answer to that, but let's apply a similar methodology. We'll let y be equal to log of x. And now, how do we simplify this? Well, we can apply the exponentiation operator and then apply the differentiation operator. So exponentiating this equation gives e to the y equals e to the log of x. That is, x. Now, assuming that we know how to differentiate exponentials, we can apply the differentiation operator. And on the left, we'll obtain e to the y dy. On the right, dx. Manipulating differentials to solve gives 1 over x. as the derivative. And so we see that if you know the derivative of log, you can compute the derivative of the exponential. If you know the derivative of the exponential, you could likewise compute the derivative of the log. But that's not all we can do. If asked to compute the derivative of arcsine, how would we proceed? What would the appropriate operator be? It's pretty clear that sine is what we want to use to feed into the derivative. For example, if we let y be equal to arcsine of x and apply the sine operator to both sides, what do we get? Well, on the left, sine of y. On the right, because arcsine is the inverse of sine, we obtain simply x. And now, because we know the derivative of sine, this is going to be pretty easy. We get cosine of y dy equals dx. And manipulating to obtain dy dx, we get 1 over the cosine of y. That is the secant of y. Now, that is not exactly the form of the answer that we want. So we need to do a little bit of trigonometric manipulation. Given the right triangle with angle y, since the sine of y is equal to x, we could assume that the opposite side length is x and the hypotenuse is 1, meaning that the adjacent side length is root 1 minus x squared. This allows us to compute the secant as 1 over the square root of 1 minus x squared, and that indeed is the derivative of arcsine. You can derive many other similar results using this same principle. You can compute the derivative of arccosine, of arctangent. You can even compute the derivatives of the inverses to the hyperbolic trig functions, arcsinch, arccosh, and arctanch. And it's not only derivatives that one can compute using these methods. Operators are very versatile and helpful across mathematics. Let's do an example involving a limit. Compute the limit as x goes to infinity of quantity 1 plus a over x to the x power. Here, a is a constant. And note the difficulty implicit here. X is going to infinity, so the term within the parentheses is going to 1, but you're raising this to higher and higher powers. You might be tempted to say that this limit is 1 to the infinity, which seems like it ought to be 1, but that is not applicable. Let's see what that limit is. We're going to, as before, let y be defined as quantity 1 plus a over x to the xth power. And before applying the limit operator, we're going to apply something else. In this case, the natural logarithm to pull down that exponent of x. On the left, we obtain log of y. On the right, using what we know about logarithms, we obtain x times the log of 1 plus a over x. Now we have something that we can work with. We're not differentiating. We are taking a limit. On the left is close to something we want to get, the limit of log of y. On the right, we have the limit as x goes to infinity of x times log of 1 plus a over x. Now, how is this helping us at all? Well, the logarithm is in the form log of 1 plus something that becomes very small as x goes to infinity. So we can use our Taylor expansion and rewrite that as a over x plus something in big O of 1 over x squared. That limit is going to be easy to compute. The leading order term is, in fact, a, and that is the limit, not of y, but of log of y. And so, exponentiating this equation and exchanging with the limit gives the limit as x goes to infinity of e to the log of y, that is y, is e to the a. And that is indeed what the limit of 1 plus a over x to the x is. Now step back for a moment and look at what we've done. We had a challenging limit to compute, a limit that we could not figure out directly. And so we took an indirect route by applying the natural logarithm operator, then taking a limit, then applying the exponentiation operator. The wonderful thing is that we can exchange these with limits in this case and take the long way around to get to where we want to go. Let's look at another example. This one seems intimidating. What is the derivative of x to the x? We're going to follow the same path as before. Let y be equal to x to the x. How do we simplify that exponent? Clearly, the natural logarithm is what we're going to want to use. When we apply the natural log, we obtain on the left log of y, and on the right x times log of x. Now we can differentiate. On the left, we'll obtain dy over y. On the right, using the product rule, we get x over x plus log of x dx. That simplifies a little bit. Doing some algebra gives us that dy dx equals y times quantity, 1 plus log of x. Replacing that y with x to the x shows us that the derivative of x to the x is x to the x times quantity, 1 plus log of x. Now that was easy enough to compute, but let's think. This function, x to the x, is super exponential. It's bigger than the exponential function. And when we compute its derivative, it's even larger than x to the x. It is of order, big O, x to the x times log of x. Now, if we think about what happens when we differentiate functions and look at their growth rates, if I take something that is super exponential in its growth rate and differentiate it, I'm losing control over the growth rate. The growth rate is potentially much larger, as we saw in the example of x to the x going to something that was in big O of x to the x times log of x. The moral of this lesson is that no matter how difficult the differentiation problem looks, taking advantage of operators is going to help you with a tricky computation.
And so ends Chapter 2 on differentiation. We've come a long way from thinking about a derivative as a slope. Indeed, we've considered derivatives from the point of view of Taylor series and asymptotics. We've considered differentials and, ultimately, differentiation as an operator. We'll begin our next chapter, Chapter 3, by inverting that operator and looking at integration.